My sweet fizzheads! To find the moment of inertia, or the rotational inertia, for a solid sphere about its center of mass, where the sphere has a radius r and mass m, we'll plan to use the definition that the rotational inertia is the integral of r squared dm. Remember, r is the distance from the axis of rotation to some little element of mass. We're also going to use spherical coordinates, where a position in space is defined as a distance from an origin, r, some angle from the positive x-axis, counterclockwise being positive, we'll call that theta, and then another angle from the positive z-axis. Rotating down from the positive z-axis, that'll be phi. Now the tough part is when we define a little element of mass, that's going to be a mass density times an element of volume. And the hardest thing to picture is getting that volume element set up. So I've tried to draw a picture here for you, and it's tough to visualize things in 3 dimensions, of course, but if we're moving away from the origin along r, then a little volume element, a little distance really, is dr. If we're sweeping out a little arc in the xy plane, and you'll see an r perpendicular and then a little arc, that little length will be r perpendicular d theta. Okay? Now r perpendicular is r times the sine of phi, and I tried to indicate that to you in the drawing as well. Now, if we're sweeping out a little arc used by changing phi, that distance, sort of by a definition of arc length, is r d phi. Now when you put all that together, multiply each of those 3 sides together to get a small volume, and rearrange things, you'll see that the element of volume is r squared dr sine of phi d phi times d theta. And the volume mass density is the total mass, m, divided by the volume of a sphere, which is 4/3 pi r cubed. Now, given those 2 pieces, we'll be able to plug those into the integral and integrate over r as it goes from 0 to the radius of the sphere, so little r as it goes from 0 to the radius of the sphere, capital R. If you sweep out theta from 0 to 2 pi, and phi from just 0 to pi, will cover the whole sphere. Alright, so on this second page, I write out some of what I just discussed in terms of getting the density and the element of volume written out. And we now plug those into this integral and apply those appropriate limits. Rearranging is what you see at the very bottom. We can factor out the constant volume density, and then I do 2 of the integrals right here. So integrating from 0 to capital R of r to the 4th, when you collect all the r stuff, dr, you get r to the 5th over 5. And the last part, integrating d theta from 0 to 2 pi, gives you 2 pi. Now, you might have to go back and rethink through some of your basic calculus tricks to evaluate sine cubed phi d phi. And I do that on the next page. Okay, my sweet fizzheads. So at the very top of this 3rd page, you'll see that I just plugged in the results. Okay, so if you simplify, you'll see at the top that the rotational inertia for a sphere, a solid sphere, of mass m, radius r, is 2/5 mr squared. Now evaluating that other piece of the integral from 0 to pi of sine cubed, where I said you might have to remember some tricks from basic calculus. and that is to evaluate sine cubed, we'll rewrite that as sine squared times sine. Replace sine squared with 1 minus cosine squared. Distribute, and then split that into two separate integrals. The first part, you'll see, is relatively straightforward. Integral of sine phi d phi is just negative cosine. The second part, do a little u substitution. You have to be careful of the signs, SIGNs here. But with that u substitution, you'll find that we've got a final value for this integral of 4/3, which is what's plugged in up top. So hopefully the work is relatively clear so you can see that. The point I wanted to make is that this process, using spherical coordinates, is much easier than trying to do the same calculation using rectangular coordinates. And that's why I shared it with you. So there you have it.